In this PowerPoint, we are going to be looking at infixes. The N5 course specification states, straight chain and branched alkenes can be systematically named, indicating the position of the double bond from structural formula containing no more than 8 carbon atoms in the longest chain. Molecular formulae can be written and structural formulae can be drawn from the systematic names of the straight-chained and branched alkenes containing no more than 8 carbons in the longest chain. So what we are doing in this session is we are looking at the first part of that, where we're looking at how you draw an alkene where the double bond is not perhaps in the first location but could be anywhere within the molecule. So in other words, let's make this simpler. What you are going to be trying to achieve today, our aim for today, is to understand that alkenes sometimes need an infix stated, understand when they are required, be able to systematically name alkenes up to 8 carbons long with infixes, and when you don't need them, without, and be able to draw any alkene up to 8 carbons long. So what is an infix? An infix is a number to tell you where the double bond goes in an alkene. For example, butene. Can I just point out that butene, the way this is written just now, does not actually show an infix. But I want to show you why an infix is required and what an infix is. So butene, if we were to draw the full structural formula of butene, it would have how many carbons? 4. It would have 4 carbons. So 1, 2, 3, 4. Remember, when we draw full structural formula, you always draw the carbon backbone. So it contains 4 carbons joined together. It's an alkene because of that little E there, and it says ene at the end. So we have to have a double bond. So can you see that I could put the double bond here as you've been shown before, but I could have also drawn it here where you had seen it previously. Now, so I'm going to draw it in this first position here, okay, after carbon 1. I'm going to draw the rest of the formula, the structure of the formula, by putting in the correct number of bonds. Carbon always has 4 bonds, so we've got 2 bonds around that carbon here. So the third bond can go there, the fourth bond can go there. This second carbon has 2 bonds here, 1 bond there, 2 bonds there, and a third bond there. So I'm going to put a fourth bond either above or below. I'm going to draw it above. The third carbon over, I've got 1 bond here, I've got another bond here, so that's 2 bonds. So I'm going to draw a bond above and a bond below, so that's 4 bonds around that carbon. And this last carbon, I'm going to add 3 extra bonds because there is already 1. And if I place my hydrogens round about it, I have the full structural formula for butene. But like I stated, butene could also have the double bond after the second carbon. So I'm going to draw butene again, but I'm going to put the double bond after the second carbon. So we've got 1 bond here, 2 bonds, 3 bonds, 4 bonds. The second carbon has got 3 bonds, so I'm going to draw another bond just to be different. I'm going to put a hydrogen there. The third carbon in has 3 bonds, I'm going to draw another bond there. And then the final carbon has 1 bond, so there's another 3 bonds being drawn. I'll put the hydrogens in again. So butene basically is 2 isomers, or there is 2 isomers shown of butene. We can have the double bond after carbon 1, or we can have the double bond after carbon 2. And chemists need to know which molecule that they're talking about, or they're going to be using in experiments or as a reactant to make future products. So to state where the double bond is fixed, right? The double bond is fixed inside the molecule, we use an infix. See? It's where the double bond is fixed in the molecule. And we use a number to state where that double bond is fixed in the molecule. So where is the double bond fixed in this molecule? Well, it's fixed after carbon number 1. So we would call it but-1-ene. And this one over here, well, the double bond is fixed in this molecule after carbon number 2. So we'd call this but-2-ene. And that number that's been placed in the formula here and here, well, that's known as an infix. And remember that the aim of today is for you to understand how infixes work and be able to draw structural formula where an infix is given, or name molecules where where you've been presented with a diagram of a molecule. So do all alkenes need infixes? Well, let's consider this one here. Let's consider propene. Meth, eth, prop. If I was to draw propene, I could put a double bond here, and I'll just finish the diagram quickly. And you may be looking at this thinking, well, you can put the double bond where it's placed, but you could also put the double bond after the second carbon. Well, let's do that for a second. So what we have here is we have what looks on your screen to be two versions of propene where the double bond is here and the double bond in the other molecule is at the opposite side. Now, when you are naming alkenes where there's infixes, it's very important to number the carbons to keep the infix number as low as possible. Okay, and that is the key to understanding whether or not we need infixes or not. Okay, now say that I was to number the carbons from left to right here in blue. Okay, that would give me, this would be carbon 1, that would be carbon 2, and that would be carbon 3. If I was to number the carbons in the opposite direction in green, then that would make that carbon 1, that would make that carbon 2, and that would make that carbon 3. So to name this molecule here, I'm hoping that you can see that we would use this as carbon 1 because that's where the functional group, this double bond, is placed. And so we would call this prop-1-ene to get to that double bond, to show the infix. You wouldn't call it prop-3-ene because that's not keeping the infix number as low as possible. You always number to keep the infix number as low as possible. Let's look at this other molecule of propene. If I number it from left to right, in blue like I did the last time, well, that would be carbon 1, that would be carbon 2, and that would be carbon 3. But if I number it the other way, in green, then that would be carbon 1, that would be carbon 2, and that would be carbon 3. So remember that we try and keep the infix number as low as possible. We try and number the carbons to the functional group to keep the infix number as low as possible. So can you see the correct way of naming this would be prop-1-ene again. because there's carbon 1 joined to the double bond. So we have got basically what looks to be two different molecules, but they're actually, using systematic naming, the same thing. So that's something to be aware of, that even though you're looking at something and it looks different, it could just be a mirror image of it, or it could just be that you're looking at the molecule from the front, right? So I'm looking at this from this direction here, so there's my eye, right? And I'm looking at it from this direction, whilst in this one here I'm looking at it from the back. Okay, these things can be rotated in space. So do all alkenes need infixes? Well, what do you think? If there is only one version of propene where the double bond can only come after carbon 1, then propene technically doesn't actually need an infix. If you wrote that as your answer in an exam paper, you're still going to get a mark. But technically speaking, propene doesn't actually require an infix because there's only one place where that double bond can go, and that's after the first carbon. Okay. Right, what I would like you to do is, I would like you to try this. I would like you to draw hextuene. You might want to pause this narration just now in order to try and draw this on a bit of paper. Okay, so hextuene, how would you go about drawing it? Well, hex means 6, so you draw the carbon backbone first. 1, 2, 3, 4, 5, 6. You then put the double bond in the correct place. So that would be carbon 1, that would be carbon 2, so the double bond's going to go in there. Or if you prefer, the double bond goes in gap 2, gap 1, gap 2, it's the same idea. Okay, now you put the bonds around each carbon has 4 bonds, so 1 bond, 2 bonds, 3 bond, 4 bonds, 1 bond there, 2 bonds, 3 bonds, 4 bonds. This third carbon has got 3 bonds, so there's a 4th bond. The next carbon's got 2 bonds, there's another 2 bonds. The next carbon's got 2 bonds, so there's another 2 bonds. And the final carbon has got 1 bond, so there's another 3 bonds. And all you would do, in order to get the mark, is you would put the hydrogens round about it. Now remember that the SQA state that you are allowed to miss out 1 hydrogen and you will still get the mark. However, you'll not be allowed to miss any bonds. You must have the bonds missed out, bonds all drawn. Try your best to always draw these things right. Don't fall in the habit of, because you know there's loads of hydrogens and you can't be bothered drawing the hydrogens down, leaving the hydrogens off and then going to the next question, because trust me with this, I have seen time and time again pupils forget to put the hydrogens in on the day that they are being assessed in the exam, and they lose marks needlessly. They get the right answer except from there's no hydrogens, so make sure that you always put the hydrogens in. Okay, let's try and name this molecule. You may want to pause the narration in order to get your answer. Okay, now I just want to show you that I've actually added here a skeletal molecular diagram as well at the bottom. That's this thing here at the bottom of that diagram. And I'm just showing you that just in case it ever pops up on any questions that you need to answer. How it works is, it's a shorthand way of drawing the above molecule without drawing all the hydrogens, without drawing, literally giving the symbols for the carbons. It's just a faster way of drawing the alkene in this case. How does it work? Well, every end of the line is a carbon. So if I was to go and draw a line like that, that would be 2 carbons. If I was to go and draw a line up like that, that would be the 3rd carbon. So there's carbon 1 there, that would be carbon 2, and that would be carbon 3. And because we know it's an alkane, or an alkene in this case, a hydrocarbon, you would be able to extrapolate that there's hydrogens and bonds there around this section here and around there as well, and you would be able to draw the molecule shown at the above. But anyway, do not worry too much about it. I just thought I would introduce it. Have a little look, study it, and see if it makes sense to you. If it doesn't, you're welcome to ask me during a support session and I can work through it with you. Anyway, let's name this molecule. So you count first of all how many carbons there are. So 1, 2, 3, 4, 5, 6. So I would make a little note at the side of my page saying that we've got 6 carbons, so that's hex. I see a double bond, so again I'd make a little note in my jot or somewhere that it's going to have an ene. It's an alkene, so there's going to be an ene ending. And then I would find out which carbon is the double bond placed on. Well, if I numbered it this way, that would be carbon 1, that would be carbon 2, that would be carbon 3, 4, 5 and 6. Or if I number it the other way, that would be carbon 1, that would be carbon 2, and you can see what's going to happen here. We number in order to keep the numbers as low as possible to the functional group. The functional group in this, and I'm throwing that phrase out again, the functional group is a group of atoms that give a molecule its chemical properties. Okay, so in this case that is, the chemical properties are all due to the double bond. So to get to that double bond, to keep the numbers low, it's going to be attached to carbon 1. So in actual fact, this is hex 1-ene. I would write it then, and where I have to place my answer, neater. So hex 1-ene is my answer. Okay, well hopefully that's helped you today. I would like you to complete your notes on Infixes to see if you've achieved the learning outcomes. And remember to submit your assignment.